thank you all for coming. My name is Arna Pálsdóttir. I'm a PhD student at Cornell University, working with Dr. Jefferson Tester, who you may have seen speak this morning. Here in Iceland, I have worked with two collaborators, HS Orka HF, specifically working with Albert Albertsson, who's also over there, and Kristín Vala, and I think I saw her, yep, she's over there in the back. And at the Innovation Center in Iceland, our other collaborator, I've mostly been working with Þorsteinn Sigfússon. And today I'll be talking to you about my thesis research, which is on the selective co-extraction of metals from geothermal waters, and focusing on the case of lithium and rare earth elements. So for a short overview of what I'll be talking to you about today, I'll start with an introduction of why we are interested in lithium and rare earth elements specifically. Then we'll move on to the geothermal brine as a resource, what are the concentrations we're looking at, and what can we expect from geothermal brines. And then I'll talk about previous lithium extraction attempts from geothermal waters. I will not talk about any rare earth element extraction attempts because that, to the best of our knowledge, has not been successful yet and has not been published in any papers. And then I'll move on to the extraction and separation process that we are using, how we are applying a supercritical fluid extraction process and what that means, what are the advantages of doing that, and then I'll talk about the selective, or how we're approaching the selective co-extraction of multiple metals, and then after the selective co-extraction, the separation of those metals. And in the end, I want to touch a little bit up on the chemistry, because that's a specific interest of mine in the project, and how the chemistry of the extractants we're using affects the extraction process and the separation process. And I've included a picture here on the right side of the Reykjanes power plant, since that's the geothermal waters that we're looking at in Iceland. The Reykjanes power plant has the highest concentration of lithium in Iceland. All right, so lithium and rare earth elements. Why are we looking at these metals? There was an interesting report by the United States Department of Energy published in 2011 on critical materials. And in this report, so these are critical materials for energy generation and energy systems. In this report, both lithium and rare earth elements are defined as critical, albeit for very different reasons. Lithium, as you can see lithium, as you can see here, is an alkali metal. And in recent years, there's been a huge surge in the use and production of lithium in the world, mainly because lithium is used in lithium batteries. And lithium batteries are used in all those new fancy electric cars that we keep seeing around now, such as for Tesla. So the reason lithium is defined as critical is because we're using so much more of it right now, and we're wondering about the status of our resource. Now, rare earth elements include scandium and yttrium, and then the lanthanides that you can see here. They are critical for a very different reason. They're not used in very high or large amounts, but the purpose that they're used in, they tend to be very specific, so you can't really replace them with other metals. And if you would replace them with other rare earth elements. So for an example of the use of rare earth elements is in wind turbines. And then for the US, they're also critical because they're used for some defense purposes. And rare earth elements are not really scarce, particularly in the world, but for the US, or what they worry about is the fact that 95% of rare earth elements are sourced from China at the moment. So it's more of a geopolitical criticalness than in the source itself. All right, now let's look at the resource at hand, geothermal waters. I've outlined a range of US geothermal areas because that's kind of where we're interested in looking at this extraction. And then also the Reykjanes area in Iceland, since we have a really good relationship with HS Orka in this project. And then seawater in the lowest line. So seawater kind of serves as a basis for us. If we don't have a higher concentration in geothermal waters than we do in seawater, then why bother go to geothermal waters in some specific geothermal areas? So if we look at the middle column here, lithium, this is the lithium concentration in these waters in either separated liquids or in just the geothermal waters coming out of the wells in parts per million. And you can see what strikes me the most when I look at this is the huge range. We're going all the way from 0.1 in Yellowstone, which is basically the same as seawater, up to 130 in the Salton Sea and 250 in Fenton Hill. So there's a huge range there, and the methods that we want to develop need to be adaptable to this range. Now, if you look at the rare earth elements, so this is the cumulative concentration of all of the rare earth elements, and you saw that there was a range of elements there in parts per million again. And again, we have quite a range. We go in the Reykjanes area, the concentration is just on par with seawater, and then we go up to 0.1 ppm in Yellowstone. But what's most striking is that there's really not a lot of data in this table. So what we'd really like to see is more research done and measurements done for rare earth elements in geothermal waters. Another thing I'd like to point out here is that we are definitely not planning to try to extract from 0.1 ppm brines. We have in my group, and this is kind of out of the area that I'm looking at, but I'll talk about this a little bit. We are looking at EGS areas, so enhanced or engineered geothermal systems. And you can see that this is an enhanced geothermal system. So in this system, we have quite high concentrations. Depending on the wells we're drilling, we get different concentrations, but quite high, up to 250, which is the highest number in this table. And these enhanced geothermal systems give us access to rocks that have previously not been in contact with water. And we see that there is definitely a resource, for example, of lithium down there that we are getting into that we previously haven't gotten into in these EGS systems. And just by pumping down water, we're getting a 250 ppm here, and I'd love to see the numbers here, but we don't have them. And what we can also do is pump down liquids that enhance the concentrations that we're getting. So we can use brines or acids and bases. So this is kind of the baseline that we're working with, but we are also looking at enhancement of the concentrations in geothermal waters. And just one thing I want to mention again too is the Reykjanes area. It's a medium-high concentration, but we are working in the Reykjanes area because we have plenty of data and a lot of information about the brine and nice partners there. All right. Now here's a slide on a few lithium extraction attempts that have been done in geothermal waters in the past. Most notably, I want to point out Simple Materials, which is a company that works in the Salton Sea in California. And they use an adsorption process with gibbsite, so the lithium is absorbed onto the gibbsite. And so it's an extraction onto a solid surface. Simple Materials operates, I think, currently a pilot scale plant with by one power plant in the Salton Sea. And I think they're working on funding for a demonstration scale plant. Other research in the area has been on precipitation. There's electrodialysis research that has been performed in New Zealand, and then ion exchange resins. Now, when we started looking into the area, we started looking at the brines, and the brines that have high concentrations of lithium or elevated concentrations tend to also have elevated concentrations of other elements. So these are the brines that have high numbers of total dissolved solids, and the brines where we get situations like this, where we get scaling in pipes. So, and the materials that we are mostly worried about are silica and calcium. So for the adsorption process, the precipitation, and the ion exchange resin, in all of those cases, we have some sort of a solid surface that we are precipitating or extracting onto. And if we have scale, the scale will coat the surface and deactivate our extraction process. And in the case of the electrodialysis, in the studies that I've seen from New Zealand, calcium sulfate tends to collect at the membrane and deactivate or block the process also. Now, the reason we need to worry about scaling, like I said, is we have a lot of dissolved materials, but also all of these methods rely on the fact that we will lower the temperature and the pressure in the brine, and when we lower the temperature and pressure in the brine, we induce scaling. We induce precipitation. So what we wanted to do after looking at these methods, which was try to find a method that's less susceptible to scaling, and that moved us towards extractions across fluid interfaces instead of onto solid surfaces. And the fact that we want to be able to operate at high pressures and high temperatures leads us to supercritical fluid extraction over a normal traditional liquid-liquid extraction process. And then, of course, we want to be able to extract more than one material at the same time. All right, I'm guessing most of you know what supercritical fluids are, but just a little refresher. Supercritical fluids are fluids that have exceeded the critical point, both in temperature and pressure. So in the supercritical region, we have a fluid that has some of the characteristics of liquids and some of the characteristics of gases. And that is something we're using in our extraction process, added to the fact that we're using the high operating temperatures and pressures. Now, if we take a supercritical fluid and compare it to its liquid counterpart, we have increased mass transfer and increased diffusivity, and that helps us a lot in the extraction process, since that means that we can do the extraction with smaller volumes. So that that keeps our capital costs down. And the last thing that I want to mention about supercritical fluids is the fact, and that's the most important fact for us, is that in this supercritical region here, we have a tunability of characteristics. And most importantly for us, we can tune the solubility of organic molecules in the fluid. So the solubility of organic molecules in supercritical fluids is directly related to the density of the fluid, and the density is directly related to the pressure. So by changing the pressure in our supercritical fluid, we can control the solubility of organic molecules in the supercritical fluid. And I'll come back to this on the next slide. I also want to mention that supercritical fluid extraction is not something that we're just coming up with right now. The innovation is more on the separation side and the chemistry side. Supercritical fluid extraction is applied on a commercial scale for both the decaffeination of coffee beans, so that's the extraction of an organic molecule over to the supercritical phase, and then in uranium extraction. So that's an extraction process from wastewater where you have radioactive wastewater and you extract uranium, so a metal, over to the supercritical organic phase. All right, so this is our extraction and separation process. If we just start furthest to the left here, this is our extraction process. We have brine coming out of a separator in a geothermal power plant. We put it into an extraction column. We sparge supercritical CO2 that has a lithium extractant and a rare earth element extractant dissolved in it. We sparge it through this extraction column. In the extraction column, we have two chemical reactions. There's a reaction of the lithium extractant with lithium to forming a lithium complex, and then an extraction with the rare earth extractant and the rare earths in the brine, and they form a rare earth element complex. So this is the extraction process. That's pretty not too innovative, really. That's been done before. But what we do for the separation is that we take our system, we split it into these three pressure zones. So in the first zone, this zone here, we have a pressure that's high enough for the extraction, and after the extraction, the lithium complex and the rare earth element complex, they stay in solution on this little edge here. Now, to separate those, we use the fact that we have designed the lithium complex and the rare earth element complex to have different solubilities in the supercritical fluid. And as I mentioned before, we can control the solubility by changing the pressure in the system. So what we do is that we start by, we reduce the pressure in the system a little bit down to the solubility limit of the lithium complex. And in that way, we condense the lithium complex out of our supercritical fluid. And now we only have the rare earth element complex dissolved in our supercritical fluid. What we do next is reduce the pressure again to the third pressure zone in our system, down to the solubility or limit of the rare earth element complex, and then we condense the rare earth element complex out, and these both go to a recovery process. And now we have clean CO2 that we can recirculate or compress again and recirculate and use in this closed loop process. So our separation process is solely based on the pressure in the system. Now I want to talk to you a little bit about the chemistry now. And the chemistry, how the chemistry affects both the extraction process and the separation process. Now, if we start by talking about the separation process, or the extraction process, I guess, a little bit first, it's important for us in the extraction process that we have extractants for both the lithium and the rare earth elements that are highly soluble in supercritical CO2. For rare earth elements, we are in luck. We have this agent called tributyl phosphate with some nitric acid and water in the middle, and this is a commercially available agent, and it's highly soluble in supercritical CO2. So that's great. And it's very selective to rare earth elements. Now, for the lithium part, we want an agent that is highly selective to lithium and is also very soluble in supercritical CO2, but not as soluble as this agent. So what we did is we started looking at selective agents to start with. So this is a crown ether, more specifically called 14 crown 4, that just refers to the number of oxygens. That's 4 oxygens and 14 atoms in total that we have. And if we just look at the clean crown ether, if we skip like this functional group and this functional group, it's very selective to lithium, but sparingly soluble in supercritical CO2. So what we've done is add this fluorinated chain to the agent to make it more soluble in supercritical CO2. And what's important about this fluorinated chain is that the number of fluorines on the chain controls how soluble it is. So if we make an agent that is too soluble, it's just as soluble as this one, we can just have fewer chlorines on our chain. If it's not soluble enough, we add more fluorines. Now, why are we using C8F17 to start with? It's just because it's the cheapest agent, so that's a good starting point for us. But this is how the chemistry affects our separation process. So we're kind of controlling the separation process with the amount of fluorine we have in our agent. Now, for the extraction process, I want to highlight a single thing that both of these extractants have in common, which is the fact that the outside of these molecules is neutral, which is good for us because we want to dissolve these molecules in nonpolar solvents. And the other thing I want to mention about the molecules is that they have a negative pool in the middle. So the oxygens here are facing towards the middle and forming sort of a negative pool where metal ions can get trapped. So if we think about this on this larger scale of our system, the solvent in our system, the CO2, is experiencing the outer neutral part of the molecule, but the metal ions, the positive metal ions, are small enough to get into this cavity and experience negative conditions and get trapped there. So that's what happens here. We get the lithium trapped in this cavity here with the oxygens, and the rare earth elements react with the nitric acid and get trapped in the negative pool that we have here. All right, and this is my last slide just on how we are tackling this problem. What I've been doing is working on synthetic chemistry, so I'm building these crown ethers. The other agent is commercially available, so we don't have to work on the chemistry there. So I'm building these crown ethers, adding different lengths of fluorous chains to them, and then I go to the lab scale. I test the solubility of the agents in supercritical CO2, test the extraction process, test extraction from different types of brines, for example, from the Reykjanes brine, and then test the separation process. And then the final part of our project will be a pilot scale test at the Reykjanes HS Orka facility, where we take our reactor and we actually hook it up to the separators in HS Orka and do a small pilot scale process. All right. So I want to thank my co-authors at Cornell, Jefferson Tester, John Thompson, and Laura Sinclair. Laura is working on the rare earth element side of this project and the leaching, and I'm working on the lithium side. And then in Iceland, I want to specifically mention Þorsteinn Sigfússon at the Innovation Center, Albert Albertsson and Kristín Vala at HS Orka, and Ríkharður Ibsen of the Geothermal Resource Park. Thank you.